Thank you. Okay. Hi, everyone. Welcome to my talk, Brief History of Binary Exploitation. We're going to be focusing on binary exploitation and not on web exploitation or logic bugs or those kind of classes of vulnerabilities. We're going to be looking at the evolution over a period of time of how software has been broken over the years, and then we're going to try to understand certain things about it. Where is it going to go? What happened over the years? And maybe try to think together about these kind of things. Just about me, some experience in the cybersecurity world. From Israel, I've been dealing with security since I'm around 15. Then I went to do the army for a bit, and then I went into a couple of companies. Today I'm working with Dart here in Singapore. Okay, so what are we going to be going over? So first of all, some definitions. What are the classes of vulnerabilities? What they are? How does it actually affect binary exploitation? Then we're going to talk about the exploitation techniques themselves and the mitigations, because, like I said in the previous slide, we're learning about exploitation via anti-exploitation, right? So we're going to look at the cat and mouse game, and I'm going to be referring to this a lot throughout the talk, on how we're trying to always mitigate and make it life harder to exploit software. Then we're going to do a summary, and then we're going to try and think together where the thing is going. So let's get into the first part. So according to NIST, which is like an organization that likes defining things, software vulnerability is a glitch, or it's a flaw in the weakness that can be leveraged and exploited by an attacker in order to gain execution in on a CPU. So when I mean execution, it means that now attacker-controlled code is now being run on a CPU. Okay, so that's what I mean when you're actually hacking or exploiting software. If we're going to look now at what people believe to be the main causes of exploitation or software vulnerabilities is a very important part. There's a difference between an exploit technique and a software vulnerability. A software vulnerability is where a glitch in the software, it's a mistake. An exploit is taking that mistake and leveraging it to execute malicious or intent of code. So over the years, we all know the programming languages, that started. We have assembly in the beginning, and then it evolved into other languages that came over the years. I don't know, Fortran or COBOL or whatever. And then it got to C, C++, which is basically like driving a manual car. And there's a lot of responsibility on the programmer to deal with the memory. And that's where some believe that's where the stem of vulnerabilities, that's where they are, the root of the vulnerabilities. And I think a very big part of that goes together with manually driving a car, if we want to call it like that, is the cognitive, what we call the cognitive strain during programming, in where, you're not always the sharpest. You come back from lunch break, and now you're sitting on your programming, and then you made a mistake in the code. Now, what exactly is this mistake that we're talking about? So the classes of vulnerabilities, we kind of have two big ones. This is like the academic world likes to define the two ones. We have the spatial safety-related bugs and the temporal safety-related bugs. The spatial would be when there's a breach in the memory's objects in the boundaries. Okay, so when access is done beyond the boundaries of an object in memory. And the most classic example of this is what we call the stack-based overflow or buffer overflow, or the heap-based buffer overflow. And the temporal safety-related bugs are bugs that happen when memory objects are accessed at the wrong time due to incorrect tracked memory usage, which means there was some kind of, in the event of time while the application was executing, there was an error that happens. And what are the errors? That we can see them here. Someone freed an object and then tried to use it again, or someone freed an object twice, and these vulnerabilities can be leveraged or exploited in order to take over the machine or run malicious code. Okay, so these are kind of the umbrella titles, and inside we have some categories of the classes of the vulnerabilities. Use after free would be the big one of the temporal, just as I said that the buffer overflow was on the spatial. And this is because software gets more complex. The bigger the code bases are, the more objects the programmers are managing, the harder it is to keep track of all these things, and the cognitive strain gets harder, and then this is what happens. This is what happens where we have vulnerabilities. Okay, now let's take a look at what we call the cyber kill chain. So we have 7 stages in the cyber kill chain. Today we're going to be focusing on the 4th stage, which is called the exploitation phase. And I would like to dive into the exploitation phase and kind of introduce 3 steps that it's comprised of. So in order to exploit or to gain control of a system in binary exploitation, we usually have what's called the setup phase, in where before we actually take or utilize or trigger the vulnerability that I was talking about before inside a program that someone found ahead of time, we do what's called the setup phase, in where we kind of groom the memory, or we alter the memory, or we change some kind of state in the program in order to increase the chances of our successful exploitation. Okay? It really depends on the type of bug, it really depends on the software, and it really depends. There's a lot of depends in these kind of things. Every class of vulnerability has its own kind of way that we need to treat it. And this is one of the reasons where this is considered more of an art. And I mean, it is a science, and actually formally it's been researched in the academic world under a category of something that's called weird machines, which is like Turing machines that are weird because they're undefined. So in these state of machines, we need to know how to convert a bug to actual code execution. So in this stage, we have the setup of the memory, we have the trigger of the vulnerability, and then we have the exploitation technique, which takes that trigger, like that vulnerability, and converts it into code execution. There's another method that has been spoken about on the internet, which is the exploitation technique. Is actually, the first stage is we have a little area where we can exploit a vulnerability, but it's a small thing. The next stage is to create what we call read-write primitive. That would be the middle one. And then the third one would be to convert the read-write primitive to a full remote code execution. But this is kind of the theory behind it. Okay, so now that we've kind of defined what are software vulnerabilities and kind of set up a language for us to discuss the exploitation techniques and the mitigations that came up over the years. And now we're going to kind of be talking a cat and mouse game. Now, if you can look on the screen, there's a little shield and there's a sword. So when I'll be talking about an exploitation technique, you'll see the sword. And then when I'm talking about a defense, you'll see the shield. And that's how the bad guys and the good guys are fighting each other in this eternal battle. Just a little recap over the last 30 years on this kind of thing. It all kind of started in 1996 with code injection attacks. And then something that defenses started coming out, but one of the big pivotal ones was in 2002. It's called the NXPID. We're going to be talking about every phase of this timeline in depth in this chapter. All right, so let's just get into it. Okay, so what is another kind of definition before? What is remote code execution? So consider this little dummy program, and on the right-hand side we have what we call a CFG, a control flow graph. This is a dummy representation of software. It's not this program's, okay? It's just a random graph that I generated for the example. It's not accurate. The point is that every little node here represents what we call a basic block. When you decompile software, you get basic blocks, which are just essential logic blobs of assembly that end with a ret call or jump, which is like it's called a transition instruction in the CPU. So, and that's how you get a graph, which means the nodes connect each other by calling each other, and that's how you basically implement logic. So the CFG is very essential for this talk. You can see that we have 4 jumps are green arrows, and the purple arrow is a backward jump. Now the attacker has or us as users, we input data into software, And then when we talk about exploitation technique, we see that red node here that was added, which wasn't in the graph ahead of time. So that's what the attacker is always trying to do. He's trying to add another node to the graph and then divert the execution to it. A funny note here. Okay, let's continue. This piece of code was generated by ChatGPT. I asked it to give me an example. I asked it to generate a code that is exploitable and generate the exploit itself, okay? This is kind of interesting. I'm going to go to the next slide, and then I'll tell you what ChatGPT did. Okay, so now we have the sword, right? So the first, in 1996, Aleph 1 introduced an article in the Frac magazine, I think it was, in where he kind of formalized code injection or stack-based buffer overflow attacks. This kind of changed a lot of things on the internet. People started looking for these bugs in software, in where we have the stack. It's a data structure in programs. We have heap and stack and the memory and the programs, excuse me. And then what the attacker does is there isn't a bounds check on the input that's received from the user, so it just copies over the data and then it starts overrunning the arguments on the stack. So when I asked ChatGPT to exploit this software, what it did was it inserted, and I told it to give me a shell code that triggers the int3, which means the debugger directive in assembly. And what it did is that it gave, this is my example, but it gave 8 or 9 A's, and then it put the CC byte. Now that is a fundamental misconception of how you exploit bugs, but it was interesting that it knew how to append the CC to the end of the buffer. So it knew, ChatGPT knew how to put a shell code at the end of the buffer that would crash the program, but it didn't fundamentally understand the fundamentals of hijacking execution, which is overriding the return address in stack-based overflows. So the reason I brought that up is that because this is the point of this slide, is to show you how the attackers would exploit these kind of bugs. What they would do is they would insert random data that would fill the buffer up, and then they would put an address on that will divert the execution. So when as we saw in the graph before, the backward edge is now executed by the CPU, the destination address is a different one. Usually in these programs, it was always stationary in the memory. We'll talk about this later. But because the attacker couldn't really know where exactly is in the memory, so they devised a technique called NOP sleds, which you can see there, which it gives him a kind of flexibility in the statistics of what address he's going to land on. And then ultimately he runs the shell code, which is what we always want to do as attackers. Okay, cool. So now that we have this, so now the world was like, oh, what's going to happen? I mean, we have buffer overflows in the world. People are attacking software left, right, and center. So engineers sat down. There were some propositions which I won't be talking about. I'll just mention them now. There was stack canaries they introduced, and all kinds of variants, or stack cookies they called them, which were trying to throttle these vulnerabilities. The problem with those defenses is they were always bypassable. You can either, by numerous techniques, you can like overrun the buffer on the opposite direction, or you can leak this cookie ahead of time and then prepare it properly. There's all kinds of ways of bypassing them, so they're not hermetic. It doesn't really solve the code injection problem. So what is fundamental to this attack? The shell code is executed from the memory that's called the stack. So the engineer said, okay, I think it was the people in AMD who introduced in 2002 what we call the NX bit, okay, so shield, in where we can now signal to a memory page that it is not allowed to be executed by the CPU. So the moment that the CPU loads that memory in order to execute it, it checks the bit. This is implemented in the page table entry, I think. And then the moment that the bit is it's either writable or executable, and not both. It's mutual exclusive. And then if it's executable, and if it's only write, so it would create an exception and throttle the execution. And that's how we get a world that we live in that we can't ever execute code anymore from the stack. Yay, everyone's happy. So we had buffer overflows, injection code. Now we can't run it off the stack. Great, the good guys are winning. The world is safe. Okay, so this held on. I mean, actually, if you look chronologically, it was like really close. But there's different versions of what came out when. But let's say officially in 2007. So this was 2002, 2000 or 2006. We had a new technique was introduced. So the concept behind this is that if you're not allowed to run code of your own that's in the memory, why don't you use the code that is already there? So think about it like in a real world where ransom letters are sent to people. So usually the ransom people, they go and they take a newspaper and they cut out the letters from the newspaper and then they build a new sentence. And why do they do that? Because they don't have their own signature or their own thing on the thing. And then so they make a new word out of existing words from a newspaper and they send the letter like this. Same concept here. If we can just use the code that's already there in the program, why don't we just chain it together and execute code? So first of all, a paper came out in 2006 that proved that this was Turing complete, so you can actually run any program that you want using this method. The little snippets of code that I was referring to, in this language we call them gadgets. Okay, so you have little gadgets that the attacker now has to like piece together, and then it derived from this code reuse family of attacks. We have three types of mini families, or three types of abusing of the x86 language, which is called ROP, JOP, and COP. The difference is what execution directive we utilize when we commit this attack. So every gadget in ROP, when you do ROP, so every gadget ends with a ret. What does a ret do? It looks at the stack, it pops the address, and it diverts execution to there. But not always we control the stack. Maybe we control only the heap. So in this address, in this instance, maybe we'll use a jump-oriented programming or a call-oriented programming, which would always use a different kind of gadget. Just to illustrate a bit of what I was talking about. So in this instance, let's say the attacker can inject code into the stack. So he's not injecting shell code anymore. What he is doing is he's injecting addresses of existing gadgets in the memory. And then the CPU is going to return to one of them. And then it would say, OK, so take the next address from the stack, put in EAX, and then return to the next one. And this is how it kind of jumps in and out from the stack into little gadgets that are there in the memory. Something that's interesting to note is that the attacker needs to assume where these gadgets are ahead of time. Okay, so he needs to put the addresses on the stack, valid addresses to where his gadgets are. So a new defense was introduced in order to throttle these types of attacks that we call ASLR. The idea behind it is, why don't we just randomize the memory every time there's an execution? So between the runs of the program, the memory isn't the same, and therefore the attacker can't assume where the memory is. It's a nice idea. It's a great idea. Unfortunately, chaining together or utilizing a different kind of attack with the existing vulnerability so this does mean that the attacker needs to have two vulnerabilities, but these types of vulnerabilities are a bit easier to come by, where the attacker can disclose and kind of learn the memory and infer how the memory looks before he triggers. So this is like on the setup stage. Remember I was talking about the exploitation phase? So he can kind of trigger another vulnerability or kind of try and infer how the memory looks. Then he can set up his ROP chain, what we call, and then he can trigger the bug and then divert execution to his code. So it's a good technique and it's worth mentioning, but it didn't really solve the problem. So engineers got back to the board, and a new family of or ideas in the academic world called CFI started emerging. So control flow integrity. The idea here is that same as before, we have the forward edge and we have the backward edge in purple. And what we want to do is we want to enforce a policy onto this control flow graph that makes sure that it's running according to what the programmer intended it to do. So if we think for a second, in ROP, what is the discrepancy when ROP executes according to this graph? So let's say E is going back to C, right? You see the little purple arrow there? So in ROP, it won't go back to C. It will go back to the middle of B, or it will go back to the middle of D, or just in the middle of somewhere in the memory. And that discrepancy is something that using CFI, you can identify and kill and stop. So over the years now, we've had a couple of solutions that are trying to implement CFI. I will just talk about two of them, one in software and one in hardware. In software, we have Microsoft, who has what we call CFG, which has evolved already now to something called XFG, Extended something Guard. And we had backward edge, so they tried to do called RFG, but actually they never even implemented it, never reached production because they found faults in it before it even hit, became mature enough to run. But the idea is that every time a indirect call or jump is executed, we validate it. Okay, it's very similar actually to I'll just go on to the next solution, and because they're very similar in what they do. Intel came out in 2016 with a proposition to do something that they call CET, Control Flow Enforcement Technology, in where they want to do the same thing that I discussed before, but just in the hardware. Now remember, we spoke in the beginning, we had code injection attack, and then we had like stack canaries, we had things that they tried to implement in software, but they weren't that good. But then the NX bit came, which was in hardware, and that really changed the game. So similarly here, people are already discussing that the CET technology is already raising the bar. And I think this is something that we should take a second to appreciate, in where when these things are implemented in hardware, we see a major shift in our world and the way these solutions actually interact and secure our programs. So what CET does is for the forward edge security, it validates every jump and call by ahead of time. You need to put in the beginning of the basic blocks, you need to put little markers inside the binary. Okay, so this is in compile time. And then what the CPU does is that it goes and when it's about to execute an indirect branch, it goes and it validates that the marker's there. If there's no marker where it's going to jump to, it will kill the program. So if a ROP gadget now is diverting, ROP is not a good example here. If a call gadget or a jump gadget is now trying to utilize somewhere in the memory and there's no marker there, then he won't be able to use it. So that means that now there's a reduction in the number of available gadgets to the attackers. That's something that makes it way harder to exploit the software. And on the backward edge, what Intel did in CT is that they have a shadows stack. So every time you have, as the program executes, so we have a stack that we used, which we discussed in the beginning, and they actually keep a copy of it in an inaccessible place in the hardware. And then every time you commit a return, it just compares the addresses, and then if the attacker tried to overrun the software, the one that's in the program, it will validate it and throw the program. The concept is that if it's in hardware, it's inaccessible. Well, not always. That's exactly the. So the attackers will have to find a way to kind of alter the shadow stack, but it's yet to see. Okay. So everyone in the research community was saying, okay, CET, CFI, these kind of things are going nicely. It looks like our defenses are getting stronger. However, already in the same year, I think a university in Darmstadt by Schuster, a paper came out about introducing advanced code reuse attacks. Okay, so we had code injection, code reuse, now we have advanced code reuse. The idea here was to abuse the semantics of the C++ language by abusing virtual tables, in where the attacker sets up the memory in a way that he can set up his own objects and then divert execution to different virtual functions that they have an effect on the program. Let's put that aside. Consider now if once he finds this a gadget that executes these snippets of these functions, these virtual functions in runtime, the attacker is conferring to the CFI policy. That's the main point here. So even he's not jumping to middle of code, he's not jumping to anywhere, he's actually jumping, he's executing normal code of the program just according to his own order. And then the side effect of those things has been proven to be Turing complete. That's what this research paper does. And again, we're kind of like back in the story of the advanced code reuse attacks. Another, the advanced code reuse attacks have two kind of families. This is on the execution, but then a new kind of family also came up in what we call data-oriented programming. So I know now we talked about we have the CFG, we have to confirm to the CFG. We're not allowed to break out of the little nodes that we discussed. So if we can't break out of the nodes, what else can we affect in the program? So maybe we can affect the actual data that's inside. We can write to certain things. There's actually there's a nice exploit in Internet Explorer 11, which was called God mode, I think. All you had to do was change one bit on an object in memory, and then you can execute whatever you want. So that was actually, implicitly, that was the first data-oriented programming exploit that was out there in the wild, in where an attacker, all he had to do was change one bit, and then he can do whatever he wanted. So similarly here, you don't always have to hijack the execution or do like very hard manipulations on the memory. Maybe you can find something a bit more interesting. So for example, with data-oriented programming, you can kind of, read the memory of the program from remote. It was also proved to be Turing complete. So let's say if you find it on a web server, you can maybe leak the private keys, like something similar to Heartbleed, using these kind of techniques. So you confer completely to the graph. You find the function that reads the certificate, and you find the function that sends into a socket, and you define, using data manipulations, only the addresses where it's going to send, and then you call those functions with a virtual table, like with the previous example that we discussed with co-op. Another example would be maybe all you can do is alter a path of a DLL that the program dynamically loads, and then you can make it load a remote DLL by just manipulating the data of the program. Okay, so this is kind of like the latest techniques that are being discussed these days. And now I'm going to discuss the last two techniques of the defense world. Again, here we have ARM leading it, actually, which is a very interesting concept. How come it's been implemented in ARM, even though in the last two we saw them implement in x86? What we do here is a fundamental thing is that in all the exploits that we've been looking at, always pointers are being changed. That's what the attackers are doing. The attackers are finding vulnerabilities, and then they're somehow manipulating the memory and changing pointers. Doesn't matter if it's a code injection, code reuse, or even in the advanced, he's still creating objects or utilizing objects and changing pointers to them. So what ARM does is it says, if you want to use a pointer now, you need to sign it. You cannot use it there's no such thing as using pointers now without signing them. So every pointer has a little structure that's added to it. So in 64 bits, they add, I think, 4 bits of a signature, and then it's validated by the CPU in runtime. And if the attacker cannot generate pointers, he can't use anything, and he can't divert execution, and then also co-op gets throttled in this attack. Another mechanism, which is kind of similar, but it's a bit different, is what we call memory tagging. So instead of creating pointers, all we're doing now is saying that if a pointer was created, it has to point to this buffer in memory. So in the first example, we can see that it's pointing to the green. And then later on, this is a spatial overflow, just like we discussed. So the pointer at point 17 will point to the pink side, and there's a mismatch, and therefore the memory tagging extension would kill the program. Similarly to the second example, we have a use after free scenario, which is the the temporal class of bugs, in where a memory was now deleted, and then what happens is the memory tagging extension marks that area as unused anymore in the hardware, and now when it's used again, it doesn't let you do it. So it's two approaches in the extension at the hardware level, but they're both aimed at killing all or solving the pointer control issue that we have in software. Okay, so something interesting to discuss is that the life cycle of phones, or mobile phones, is way shorter, and therefore we might see these kind of techniques implemented way more quicker in mobile devices as opposed to PC, where the software stuff is only introduced once in 15 years or something like that. Because we had 2002, the NX bit, and then we had 2016 when they brought in CET, and it hasn't even been deployed yet to the hardware, to our actual computers. So that's something to discuss, and we'll talk about what's next. Okay, so to kind of summarize what we've discussed now, so we have Jerry, who represents exploitation techniques. We discussed the code injection, the code reuse, and the advanced. And then we looked at all the defenses that came out during the years, right? We didn't discuss the SELP, but we discussed all these advanced defenses. And together we get the cat and mouse game over the past 30 years of how we're trying to throttle the binary exploitation world and make our software safer. Yep. Okay, so now let's kind of try and think together and see where this thing is going. So I think I mentioned a lot during the conversation on the fundamental difference between hardware-based mitigation, exploit mitigation, and software-based exploit mitigations. I think it's fundamental and very important for it to be able to be observable. And what I mean by saying if something is observable, it's actually very similar to psychoanalysis. When you cannot infer things on yourself, sometimes you need someone else to look at you and then see that something wrong is going, or another model to actually identify that something is happening, which means introspection in software cannot really act as in the security world. There's a model now being developed, I don't remember by who, it's called the Cherry model. They're trying to implement all these exploit mitigation in a hardware model, and then hopefully in the future, every motherboard will have the CPU, and then we'll have another CPU that's in charge of doing all these validations as it executes. So the fundamental point here is that the hardware separation gives us the ability to observe software as it executes, and then we can kind of understand that something wrong is happening. Will these vulnerabilities ever cease to exist? So as the world evolves, I mean, I think it's way harder to, if in the 90s, in 95, I mean, one person can sit at home, find a vulnerability, exploit it, and create havoc in the world. Today, we're looking at something it's way harder. You have groups of people, a lot of funds being invested in these things. It's a very big project in order to exploit software today. I mean, let's just take a browser if you want to exploit Google Chrome today. So you need to have a lot of resources and research and put a lot of effort. So I think it's way harder today to exploit software bugs, and the bar of entry is way higher. But of course, it's always going to be doable. That's for sure. And I think the next point would be the mobile world versus the PC world. I discussed that regarding the point authentication and that kind of stuff. I can just actually simply ask the question: when will point authentication and memory tagging enter x86 architecture or the PC architecture? And then if we kind of try and think and say, oh, maybe the hardware cycles are longer, so it's going to take longer to enter. So then it means that the mobile world is much more agile, because assuming that hardware has to be the place where you can actually solve these problems, the mobile world has a shorter life cycle in the hardware, and therefore that will be more eligible to have stronger defenses there. Yeah, that kind of sums it up, guys. So So first of all, thank you for listening. And second of all, does anyone have discussions, questions, or anything else?
Hi, so if anyone has any questions for Shlomi, please raise your hands and I will hand you the mic.
Hey Shlomi, thanks for the presentation. My name is Vitaly. I have a question, actually two of them. One is when you talk about Turing completeness in regards with the ROP or DOP, like data object programming, then how do you even prove that? Don't you need special gadgets to exist to prove the completeness?
Yeah.
Does it mean that it actually is relative to the actual program, and not every exploit, not every ROP can be Turing complete?
Okay, so yeah, sure. So the people who, so there's a paper to it, and I'll be more than happy to discuss. It's not this paper; it's a different one regarding DOP, data-oriented programming, in where in order to prove something that's string complete, you need to be able to move something in memory and commit and perform a shift on it or something. Like there's a very, very basic definition. Now, in their method, they proved that, yeah, you need to have what they call the loop gadget. This is what you see here, the MLG. And assuming you have a loop gadget, then you can always find the other gadgets that will perform for you the move and the shift. Yeah. So
it is possible that not every application, not every code may actually have these gadgets.
That's a very good question. So assuming the program isn't big enough.
Yeah.
Yeah. So
maybe not even big enough, but also contains these gadgets. So if your compiler deliberately removes such
yes,
side products, then
I think there was something that did that for. There was an extension for CLang to throttle this thing.
I see.
I can't remember the name of the extension.
Okay.
Do you know it, maybe?
No, not really.
Okay.
But I was just curious. Another question is, you already touched ChatGPT in your presentation. So do you see that it may be a game changer? Maybe if not now, that in the future? What do you see? How is it going to change the language?
I'll be happy to answer that. I've been doing some research unrelated to what we spoke about now, and then I'll share some thoughts that happened. So what I was doing is some reversing in Android, okay? So I was given a function, and, or I don't know, I was going through things, and I don't know, there was a function there, and I didn't really want to understand. I took the function from the decompiler, put it in ChatGPT, and it just answered gave me exactly, it made my life really, really easy, okay? So that was amazing. But then I wanted to do something, I've been actually wanting to generate software, and I haven't received a working, no, I have, but like for my purposes, I needed it to use special classes in Java or something like that, and it didn't give me something that actually worked without me having to spend more time and get it to work. So out of the box, it didn't give me something that can just, all right, Mr. ChatGPT, please give me a module. I needed to implement, RSA using bouncy castle with this parameter, and the code didn't work. But when I asked it to infer something about some engine that I was looking at, it understood something very, very fundamental, which I completely missed. So I think on the research side, it's very, very strong, and it will show you more knowledge on things that you don't know. But when it needs to generate things that you can actually use for production, I'm not sure I would. I don't think we're there yet. Obviously, we're going to get there in the next years, for sure.
All right, thank you.
Yeah, thanks for your time.
Any other questions? Okay, if not, can we just give Shlomi a round of applause?
Yeah, thank you very much.
Very insightful.
Thank you.